Motors. Everyone loves controlling motors, so let's control lots of motors. Got a great big drill motor. We've got a standard 4-wire stepper motor. We've got one of these little fun eBay $2 or $3 jobbies that perfectly meshes with one of these little tires. Great for little robot tires. This is a DC motor with a gearbox. We've got a servo motor. Now this is a little servo motor that could in theory be powered right off the Arduino, but we're not going to do it that way. Well, we'll do it once that way and then once with a separate power supply, because normally you can't get enough power out of an Arduino to do much. So you need things to have their own power supply, and with larger servo motors you would need that. And then we've got a little DC motor. And we're going to control all of these motors with a variety of technologies. One I've already done a video on, but we'll do it in more detail, is the L298N. It's a nice little controller module. Now you can buy the 298N chip by itself, of course, put that in your projects, but this module makes things quite convenient. And it will control either one stepper motor or 2 DC motors. And it has a few other features, but you can put quite a few volts in here, about 35 volts in, 2 amps per side, out to a maximum of about 20 watts, and that would be more the heat dissipation. So that means you can't put a 2 amp 35 volt motor in, because that would go way over the 20 watts. So a 10 volt 2 amp motor would in theory be the highest you could do, or some other combination that gets you up to 20 watts. Then we're going to use a motor control shield. This uses 2 L293Ds, which are pretty well absolute standards in the world of small motor control. This particular shield, since it has 2, these are what are called H bridges, which allow you to spin a motor one way, spin a motor the other way, or in the case of a stepper motor control, you can use one 293D to control one stepper motor on one side, and you could use a 293 to control the stepper motor on the other side. This particular shield's nice because the 293Ds are replaceable. And 293Ds are not the most robust chips in the world. They can't handle a lot of wattage. I forget the specs on it, but let's just leave it at not much. So they'll burn out, and this board has nice replaceable chips so that you can replace the 293Ds, which are cheap as dirt. And then we're also going to use just a 293D in its raw form. Now, on circuits like this, you can see some capacitors. They're good for smoothing. There's some other little diodes and whatnot that help protect the motors from sending power back into your circuit and whatnot. But we're going to show you the H bridge in its raw form. We're going to really put no other protections in for now, and that way you can see the most elemental of circuits. And the first one we're going to begin with, and what I've got here is this is an Arduino Nano. I like these because they go on breadboards, and for the shield we're obviously going to have to clip that into an Uno, so we'll dig out an Uno for that one. And yeah, so the first one we're going to look at is we're going to get this all out of the way. We're going to bring in this circuit here, which is the MOSFET. And this was the first one, and we're going to be using this battery pack, this 1850 LIPO battery pack, putting out about 12 volts. And what we have here is we've got a very simple Arduino sketch. Has 2 pinouts, one of which is just to pin 13, which is the LED on the board, and the LED is just going to go on and off with each cycle, with each loop. And so we're going to begin with pin 5, and that's going to be the one that sends a control signal to the MOSFET, and it's going to write at full power, wait a second, write no power, also turn the LED on, then it's going to wait a second while it's doing that, then it's going to go to half power, turn the LED off, and wait a second, and then it'll loop back. This is commented out code, we'll use that in a moment though. and then loop back and turn the thing on. So basically it'll be on, off, half power, on, off, half power. Now the MOSFETs is, nearly all MOSFETs have the same pin configuration. Not sure we can try zooming in. See, it'll go all blurry on us. So MOSFETs, I don't know if you can quite see it here. They have 3 pins, 1, 2, and 3. And the right pin is ground. The center pin is sort of a power pin, and the third pin is like a signal pin. And so what we've got here is this is the ground negative coming in from the battery pack. This is the ground coming from both this is the ground coming in from the Arduino. See, there's coming from the ground one. And then the third red wire we have here is coming in from pin 5, digital pin 5 on the Arduino. So it's going to be basically like your finger on the light switch. And then in the middle here, we have one of the wires coming in off the DC motor. And then over here, we're just going to connect the DC motor permanently to its positive. So what this is going to be doing is turning on and off this DC motor's connection to its ground. So when we've got the Arduino set to put 0, our low signal, out of digital pin 5, this will just shut the switch off. So light switch off, no power to the Arduino. When this is set to digital right high, it's like the light switch on, power will flow through ground to ground, the motor will spin. So let's go out, and then this is just in the digital, this is the motor's positive, and I'm just putting it in there so that I can connect positive here. And as you can hear the motor spinning up, I'll just get this little, there we go, that's all connected. So now you can see the motor's doing just as I said. It's high, stop for a second, low, and just cycle round and round. So low, high, and off. Now, I don't know if this camera is going to pick up on it, but when this is on the medium, the 128, you can hear a little bit of a whine, and that's where we're actually hearing the pulses. So we'll drop this down to 80, re-upload, nope, didn't mean to do that, upload the sketch. So now the slow speed will be much slower, and as you can hear, the whining is higher, and the tape is even getting in the way. We're at the limit of what this motor can do. So it's not that 1 is the slowest speed, it's with each motor, and depending on its load, the lowest will be some number, and as I discovered, it's close to 80. So 50 can't even spin this motor. Now, if we put a good capacitor in there, we'd smooth out the flow and maybe get this motor to spin at a slightly lower number. But this isn't the only way to do this. An alternative is we can give the motor a series of kicks. As you can see here, what we're going to do is we're going to say, go to high, delay for 1 millisecond, so that's 1,000th of a second, and then for the next 45 milliseconds, do nothing. So we'll send this to the motor, and remember this is looping fairly quickly. There we go. It's now giving the motor a series of kicks. Now it's not very strong. I can stop that with very little effort with my fingers. We can speed that up by reducing the delay of the off cycle. So we drop that from 45 to 15. There we go. You can hear the pulsing, which is telling you roughly the frequency at which we now have it pulsing. We've changed and effectively created our own pulse width modulation. We're the ones turning it on and off for our own selected time. So there's a 1:5 ratio. And we'll go half and half. So it's on half the time, off half the time. And as you can see, it goes fairly nicely. Now we can make it more interesting by turning it on and off at it's on and off for a longer period of time. So there we go. And that's actually quite strong. I'm having trouble stopping that. Even though it's on half the time and off half the time, if we compare that to another one where it's on and off half the time, I can more easily stop that. So, as you can see, these things are, it's one of these things where you gotta play with it. There's no one way to do things with an Arduino. There's no right way. It totally depends on what you're doing. So, for instance, doing something like this, where I'm going to put the code up where it's only on for 1/100th ratio, and I can easily stop that with my finger. That might be appropriate for something that's more like a clock, where there's very little power required, just more precise movements. Anyway, so that's a MOSFET. Excellent way to control a motor. We're able to put out 10 volts here, or 12 volts. And so now, let's pull this motor out. Let's grab ourselves a drill motor. So what we're going to do, I just noticed the little leads are all cut off here. Quickly just build a pair of leads for this that plug nicely into the breadboard. So we've got those two. We'll bring the motor into view. Connect one of these like this. One of these like this. So now we effectively have two leads off the motor. So one lead we'll put, say, in that center, which is going to be the ground coming in through the MOSFET. And then we'll connect the other one to the positive. And when the last signal we sent was the motor to turn. Now the problem with this motor is that it is a geared motor, so even if we're turning it a bit, it won't be turning much. So let's go back to this. So 50 is quite clearly too high, or too low, sorry. And there we go. We've got a fairly robust motor. Putting my finger on the MOSFET, it's not warm at all. Heatsink's doing its job, combined with the fact that that's not really any load for this MOSFET. So a MOSFET is an excellent way to control huge amounts of power out of from a tiny little Arduino here. So the next motor we're going to be looking at is a little servo motor. They are pretty straightforward. The key to a servo motor is that they can turn and then hold a position at a very specific point. So this motor has basically 180 degrees of motion. Some servo motors have 90, some have full range of 360, but this is a pretty typical 180 degree servo motor. Now they have 3 wires. A very common coloring is brown, orange, or brown, red, and orange, sort of a yellowy orange, which I prefer to switch to yellow, red, and black. So black is ground, red is positive, and yellow is the sort of command wire. So again, I'm going to use pin 5. Pin 5 is going to be the sort of, not sense wire, sorry, the command wire, I guess would be the way to call it. And we're going to put ground into ground and 5 volts into, or the positive into 5 volts. So just the 3 wires. Now in this particular case, this little motor can take its entire power from the Arduino. And then we've got a little sketch loaded here that we'll run it through a pretty straightforward set of motions. Basically 0, 90, 180. So pretty straightforward when you're running it off the power of the Arduino. But this is a very small motor, and you couldn't even run many of these off one Arduino because you would tax the USB and the Arduino's power output. So what we're going to do is, I've got a little battery pack here which is going to put out about 5 volts. So we're just going to put the 2 wires here and here. So there's just 5 volts of positive and negative. So then we're going to pull this positive coming from here. We're going to pull this ground. Then we're going to connect a common ground from the ground that's both going to here and to the power. And then the sense wire senses per normal. Then we power up the battery pack, and now we have only one control wire going to the servo, and the rest of the power is coming from the battery pack. So now we could be running a much larger servo, or many, many servos. So again, very straightforward. Now just looking at the code, we have, shut this down, actually no, we'll leave it running. We have a very, very simple thing. We run the servo library. This is built into the Arduino IDE. Create a servo, instance of the servo class, attach that to pin 5 in this particular case, and then we write in degrees the position we want it to go to. So we'll like that. So we'll go, say, 45 and 90. Seems to be a little unhappy at 0. So, as you can see, you have near complete control over what the servo does. Some servos are faster than others, and if you wanted to go more slowly, you could have it go to each angle and wait there for a moment. And these servos are pretty cheap, but you can get very nice ones for remote control cars that are very powerful. Beautiful bearings inside and stuff. So that is a servo motor running. So now let's do a stepper motor next. Probably one of the most complicated motors that you can have. So we're going to turn the battery pack off. Pull all that out. And we're going to get our next motor, which is a stepper motor. Now, stepper motors, again, I'm not going to go into a complicated explanation. There's plenty of them online that explain how all the coils and whatnot work. But what effectively you're looking for is there's these two wires run to a pair or a series of coils. Then another two of the wires run to another series of coils. And through an interesting game of energizing and moving the sort of how the coils are energized, it's able to give a fairly controlled movement to the motor. Now, one difference between a servo motor and a stepper motor. So the servo motor, as you saw, we could set it to 45 degrees, we could set it to 180, and it'll hold that position. And within this servo motor, each time you run it, 180 is basically going to be the same position. 180 is going to be like right over here. 0 is going to be roughly over here. So it's a predictable situation. With a stepper motor, you're telling it to make steps, and you can even, with the library, have fractional steps. But the stepper motor has a certain capacity to do steps, so it's not uncommon that they're measured in how many degrees or how many steps. I think this one's about 24 steps per rotation. So you can instruct it to do one step, and it will do 1/24th of a rotation. Another step, it'll do another 24th. And if you turn a stepper motor with your fingers, you can kind of feel it pulsing underneath. And those are basically the steps. Some have gears in them to reduce the effective ratio so that it turns 24 steps internally, but then only might take 240 steps to go around in a full circle. So it gives you very fine control, but it doesn't actually know where it is. So let's say you have a 24-step motor. So in 24 steps it will return to where you started. If, as it was going through those 24 steps, you grabbed it hard so that it didn't turn for some of those steps. Let's say it started facing this little hole here, and you interrupted it part of the way through. After 24 steps, it might not have returned to its original position, and there's no internal knowledge that it's no longer out of alignment. So typically with a stepper motor, unless it's a very powerful stepper motor compared to the job you have it doing, you can never be really certain as to how its alignment is working. So often you have to have another mechanism outside of your immediate mechanics that gives you some kind of an alignment, either an optical encoder or maybe a switch that as it hits one end, if you had something moving back and forth, you could have it click a switch when it gets to one end. But there's distinct benefits to stepper motors. You get very, very fine control, especially when they're much more powerful than the mechanical task that you're asking them for. So that's why they're used in things like 3D printers and machining tools and whatnot, because if you have it set up right, you know that 24 steps, if it was a 24-step round, you know that 24 steps will have taken it back to its original position. And so 240 steps would be 10 rotations, and so on and so forth. So it can give you unbelievably precise control, but almost always you either have something continuously monitoring its position, or you have something resetting its knowledge of position. Now, what we need to do is, the color coding on these wires is not a terribly consistent color coding. This is a four wire stepper. There's all kinds of different configurations. Often they're in pairs, but even then, not always. There's some very strange ones. You can have 5 or an odd number of wires, but there's 4, 6, 8. I've never seen an 8, but they know how to exist, and they give usually ever finer control, fewer and fewer degrees per step. So this one's a 4-wire one, and we then have to determine which of these wires work in pairs, because that's how they work, is they work typically in a pair. And there's some ways you can do that with a multi-tester, and with such a low-powered motor where we're not really worried about pumping too much power into it and frying it, one of the simple techniques for figuring out which are pairs is just to try them, different combinations of mixing them up until the stepping motion works the way it should. And you have to be careful of that because, as I say, if you're putting too much power in, you could cause some problems. But this is a very low-power circuit, so getting the ordering wrong is not going to be a disaster. It'll just not step. And once you have the 4 wires correctly hooked up, it will step very, very nicely, and it'll be very clear that the stepping's working. Anyway, now we're going to wire this up, and we're going to wire this up initially to I think we're going to start out with this good old one, but we're going to do, with the stepper motor, we're going to do this one, this module here, 298N. We're going to try this with the 293D. This is pretty straightforward motor shield, and then, as I said, we'll do the bare bones 293D. Actually, we might start with the bare bones 293D right off the bat. That might be the better one. It's very simple, and this is a very low-powered stepper motor, so we don't need to worry about too much power. And then we can run it off the Nano. Well, let's wire this up. So here we have a H-bridge 293D set up with some fairly straightforward code. This is rotating 24 steps per revolution. I'm telling it to do 1 revolution one way and 1 revolution the other. So we can go up here into the code. It's pretty straightforward. We load the stepper library. We set how many steps per revolution. As I say, this particular motor is 24 steps, but it could be, some motors are even up to 200. And then it also depends on the gearing. You could have a motor which is geared to have a motor that only can do 24, but if it had a 10-to-1 gear ratio, you would potentially then get 240 steps per revolution. So then you just instruct it on how many steps to do. So we can bump the step speed up. Although there's a limit, certain motors can only then hit certain speeds. And past that speed, the motor will just start losing its mind. See, now it's not doing a full revolution because it's not able to keep track at this high speed. And that would also depend on the load. A heavier load, it's going to lose it more quickly. Let's try slightly slower speeds until we get to the Now, like with most things electronic, I would never recommend pushing them anywhere near their limit. So even if you did find the exact limit today, temperature, a bit of wear and tear on the motor, a little higher load, a little less grease, many different aspects can change what its actual maximum is. So my personal recommendation is you never push these things to their limits. You always leave some wiggle room. So if we hold this for just a moment, as you can see, the stepper loses track of where it is because it doesn't know how far it's turned. It just knows how many pulses it has sent to the motor. So we'll multiply this by 5. And now it will spin 5 times. And then go back once. So, to take a quick look at the wiring, one of the things this particular motor has is you can see a little bit of its internals. So one of the great giveaways is it didn't even have to really multi-test this to figure out which wires paired up, because you can see 2 of the wires go off into sort of an upper, beginnings of an upper coil, and 2 of the wires paired off and went into a lower coil. So you knew that these are the pairs. And quite often, but again not always, when the wires come out, they will come out roughly in order, and then these they did. So I marked these with little dots. There's 1 dot for wire 1. Can't really see the dot on wire 2. Then wires, get them in the exact order here. Wires 3 and wire 4. So once you have the pairs, worst case scenario, it was really just a matter of figuring out which of these wires was 1 and 2 versus 1 and 2, and vice versa. So just a few combinations that you had to try out, but I actually got quite lucky. So now the wiring down here is a bit confusing, but the H-bridge, I'll put out a diagram for this, but the H-bridge basically has 4 corners that all get a positive voltage of some sort. Upper left-hand corner, this is the voltage that drives its sort of thinking, and it's a 5 volt in. So I'm getting that 5 volts, bringing the Arduino positive and negative up to this top rail. Then I bring that positive down to this upper corner. I'll get something a little pointier here. So this one here is getting the 5 volts in. That's that corner. The other 3 are all getting their positive. Generally, well, the main one here is getting its positive from the battery rail. So here's my little battery pack. And this can be up to 36 volts. Then this one goes up to a common ground, which are the two middle. And then the common ground is effectively coming from the top rail, which, as I say, is the Arduino, so it goes to these two middle guys. Then the outer wires, the next one in, are where the 4 pins, so these are the blue wires, and these are the 4 control pins, which, as you can see in my code here, are pins 8, 9, 10, and 11. I've just chosen those somewhat arbitrarily. They're just a nice neat little row that was at the limit of the wires. And they go to the 1 pin in. And they're going 8 goes here, 9, 10, and 11. And then if you look here, we have the pin 1 is the kind of brown one, and the pins just go 1, 2, 3, and 4. They just go around in a circle, and it's the same. So these pins match up. And if we get the ordering wrong, the motor will do weird things. So let's just try putting the... See if we take one out. See what the motor's doing. That's only 2 of the connections. Now we'll swap these around. And the motor is working. But you'll notice which way it's turning. It's clockwise. Now it goes counterclockwise for its 5 revolutions. So as I say, you can get this actually quite close with a 4 wire stepper, and it'll kind of work. But then when you get it exactly the way you want, it will work perfectly, or it'll work perfectly backwards. So there's all kinds of configurations that will either sort of work or will work perfectly. In fact, I think that might be better. As you get into the 6 and 8 wire steppers, though, it becomes a more complicated game. The math just is working against you. So anyway, there is a stepper with an H bridge. Oh, and as I say, the diagram here is pretty straightforward. Now this stepper is being completely untaxed, but this 293D, which you can buy in packs of 10 for just a few bucks from eBay, it can handle up to 36 volts, but it can't handle that much in the way of amperage. I forget exactly what it is, but I don't think it's even close to a full amp. And there's a few tricks you can do to get more power out of it, but really there's not much. Technically, the ground pins are also considered to be heat sinks. So you can try heat sinking off those, and that'll buy you a little bit of extra wiggle room, but it's not going to double it or anything. Well, anyway, so now we will move on to the next motor. Now we're pumping quite a bit of juice into this poor little motor, so we'll probably stop soon. But we've got a battery pack here. It's that LiPo putting out 12 volts. Putting that into here. In fact, we're going to just turn this off for a moment. Don't need that much power going in. And so what we have is 12 volts goes into here. We have 4 control wires, same code that we were using before, so it's 8, 9, 10, 11. They go straight over into here. And then we just have the control, or the 4 wires for the stepper motor. They come out, and they go into here. And that's about that. It's a fairly straightforward thing. This is an L298N versus what we were using before, 293D. The D can only handle As I say, it's not a lot. It's in milliamp, it's not an amp. Whereas, and its watt dissipation is also very low, whereas this is a much more capable module, and it can handle up to 36 volts. And I don't understand, the little thing here is marked 12 volts. And interestingly enough, the module I got, zoom in here, you can see I had to resolder these three. For some brilliant reason, not only did they put this on backwards, which meant I'd have to try and feed the wires down there, but they didn't even really finish soldering it. So a couple of these posts weren't even soldered on, so this module was defective when I got it. But just unsoldered one, swapped it around, soldered these back in place. I think those look like perfectly solid solder joints. Oops, and my negative has come undone, as you can see. Very straightforward. Now, with the extra power, let's bump that up to a higher speed. So we'll upload this. And remember, the lower speed, or the lower power one at this speed, couldn't keep track of its location, it would lose. So this one's able to handle 200. Let's see if it can do 300. Seems 300's even possible. Let's go 4. $400 seems possible. Go to 6. Well, anyway, that's too much for this little motor. Too much power. So we're going to, I would say if we ran that motor for another few minutes, it would just burn out. So as I say, very, very simple wiring. These 4 go directly to these 4. 12 volts going in, common ground, and then these 4 go out to the motor. And it's really just a question of finding the proper order. So that is it for the stepper motor with this particular module. So now while we've got this wired up, let's do a DC motor. Okay, here we have 2 DC motors being controlled by this module. I left these 4 wires in place, so that's digital pins 8, 9, 10, 11 going straight over to here. We've got one DC motor connected to these 2 pins. We've got another DC motor connected to these 2 pins. And then we have a battery pack, which I have everything but the negative connected to a common ground. And as you can see, there's just this goes to the ground rail, this goes to here, positive goes into the 12 volts. And if we look at the code, it's a very simple bit of code. We'll close these. We have pins 8, 9, 10, 11 set as digital just for outputs. Then we just cycle through, turning pins 8 and then 9, 10, and 11 high, and leaving the others low with a delay of 1 second between each of the between each go. So basically what this is going to do is say to pin 8 go high while pin 9 is low and pins 10 and 11 are low. Now you can think of these as pairs. Pins 8 and 9 control one of the motors. Pins 10 and 11 control the other motor. So we have what we're effectively going to do is say spin the motor in one direction and the other motor will be off. Then we say reverse the direction, leaving the other motor off, then turn off the first motor while spinning the second motor in a different direction, leaving this one off, and then spin it around the other direction, and repeat with a 1 second delay, or it'll run it for 1 second, then run this for 1 second, and run this for 1 second in a cycle. So let's take a look and see what happens when we engage the negative pin. And there we go. They might be spinning too fast, but you can see they reverse each time. And it's a pretty straightforward bit of business. 2 motors, total control of the direction, and there's a variety of ways we can control their speed. Anyway, so what we have is we have 2 motors spinning and doing their thing, taking their power from the battery pack. Now that, of course, from the Arduino. The Arduino could never power motors like this. Motors wouldn't work, and the Arduino would get burned out. We're only using 4 pins from the Arduino, which is quite nice to keep the pin count down. Well, 5 if you count the ground. And this module's doing all the heavy lifting. Now, to go on a little bit of a tangent, one of the beauties, let's stop this, one of the beauties of this particular module is that there's one more pin here. And this pin is putting out 5 volts. That is, this module's taking in 12, which it can use out in the motors. But this last pin here is putting out 5 volts, and a nice steady 5 volts, regardless of what we put in here. Now, we have to put in more than 5 volts, 7 or so, 7.5 maybe. I forget what the drop is to the 5 volts, but as long as we're putting in a fairly okay voltage, a few volts more at least than here, we'll get 5 volts steadily out of here. So we can put 12 volts, 20 volts, 30 volts. I think this can take 35 volts. So we're looking at anything up to 35 volts, and you'll get a nice steady 5 that's coming out of here. So 12 volts, or we're putting in 12 volts right now, but anything over about 7 volts, and you're then going to get 5 steadily out of here. So we put 12 volts, 35 volts, whatever. We'll get 5 volts out of this last pin, and we can use that in a robot or whatnot to power up the Arduino, because right now we're using a USB connected to a desktop to power it up, but there's also a VN. But that VN, you've got to give it a pretty good 5 volts. Like, I don't know exactly where this thing will die, but I wouldn't be surprised if even at about 5.5 volts, bad things start happening to your Arduino. And this is a 5 volt Arduino, of course. There's 3.3s, in which this is all irrelevant, but you're certainly not going to put 12 volts into this Arduino and have it survive. The magic smoke will come out. So this 5 volts is an excellent place to this 5 volt post is an excellent place to get 5 volts. It's a good 5 volts, fairly capable, so it can run an Arduino, no problem. I forget how many milliamps it can put out, but it's a lot, so the Arduino's not going to have a problem. And then you might have other components that need 5 volts. So you can feed them the 5 volts from here, rather than, again, draining it out of your Arduino's 5 volt pin. You can just shoot 5 volts all over the place for that. Although then you'd have to start paying attention to how many milliamps capacity this has. And so there's a nice heat sink on this. So this is a great little module to throw in a robot, because, I mean, for every one of these you put in, you get a free 5 volts source. Only one place that you have to send your battery power in, so you have a nice big battery pack. And for every one of these you can have 2 motors, and of course 2 motors is often going to be the drivetrain of a very common robot technology, with most of the other bits being more things like ultrasonic sensors and whatnot, although you may have servos and other components. But if you did have servos, maybe you could run them using an L293D, because they're typically going to need a smaller amount of power, not necessarily this big beastie of a module. So that is all about this one. So as I say, this is a fairly straightforward module, though I was a bit disappointed to find this one was defective. Now, one teeny weeny thing you want to be a little bit careful of when you're wiring this up is you want to wire the power in last, because one of the things that you might not be aware of is that with most ICs that have a heatsink capacity, the heatsink is ground. So if you've got the positive wired in there, it's possible to touch one of these wires while you're manipulating, in which case you've just sent 5 volts into your Arduino through one of the pins, which it might not appreciate. So yeah, wire your positive in last, because this giant heatsink is basically a big short waiting to happen. This one has a bit of a painted on coating, so it's not so bad, but for instance when I was using this heatsink, it's just demanding that one of your wires touch it while you're assembling it. So my recommendation is don't be having this 12 volt, power source connected, because you're, well, just asking for trouble. And that's it. So we'll go on to our last module, which is going to be this one, where we have to dig out an Uno. And these are a nice module, they're clean, and they use up a whole pin selection, which is why I much prefer the smaller, sort of fewer wire components, but people do like these because they make for very, very, very simple robotics projects. And so, yeah, so let's do this one. Okay, so we've got an interesting setup here. We've got the Uno buried underneath here. This is a shield sitting on top of the Uno. This is based on the 293D, which I looked it up. It can handle 0.6 amps, so not a whole lot of power. We got a little battery pack here putting out 5 or 6 volts. It's wired in here, and then that way we're not trying to power this motor off the Uno, which has a very limited capacity, like 200 milliamps or something small, but again, you don't want to be pushing that too hard. And this could be a big battery pack, not obviously too big if this can only handle 0.6 amps. This could be a fairly big motor, but again, 0.6 amps isn't too much. So we're running some pretty straightforward code here. We're using the AF motor. It's an Adafruit library, and it gives us the ability to do steppers, which is quite nice. So we set this up. You can look up the parameters here, but pretty straightforward. We set the motor speed, and just like before, depending on how much power we have going to the motor, then the stepping speed can be set higher and higher. But if you set it too high, it'll start missing steps. Now, the beauty of the stepping library is that it has, we've got it all set here for single steps. Now we could say step in different ways here. So this is all, I'm just doing 5 steps here and then 15. And this is giving us 3 kinds of, well, really the ones you most want to concern yourself with are right here. Single steps, and that's exactly what it means. It's the ones where it's going tick, 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 like a clock. There we go. So I just do 5 back and forth. The double, it just does 2 steps at a time, nothing too miraculous there. The interleave, generally not used so much, but the microstep is quite interesting. Let's set this to 150 microsteps. And what happens is the way these motors work is it's able to generally jerk the motor to the next step, which is just a pairing of coils, or it's a series of pairs of coils, and it's able to sort of push the magnetic structure to the next critical pair. But a microstep is where it plays a nice little game with the coils, and we're actually able to get more steps out of this then there are sort of theoretical steps. This one's a 24-step thing, and I don't know how many steps we could get into this. Let's drop the speed. There, it's very slow speed. Basically one tick. So it's going to do 5 of those. You can see the size of a step. There's. And then look at those little steps. The micro steps are really small. Now, a downside to the micro steps is they're weaker. There's not as much strength in the motor because it's having to really play games to get that micro step. But it gives you very fine control, which is great when you are machining or using this as a 3D printer motor or something like that. And so it's weaker, so you need a stronger motor to move the same sort of amount of material or gearing or whatnot. But it means that if you've got a motor that doesn't have enough steps, you can buy yourself quite a few more, and depending on the power of the motor, how much power you're willing to put into it, and how much power you're willing to lose from it, you can get 1/16 of a step, which means, well, if you had a very crude servo with only 10 steps, that would buy you up to 160 steps out of that servo. So this 24-step servo, we're pushing this up to nearly 400 steps. So it's buying us a lot of precision. So that's less than a degree per microstep. Anyway, that's it. This is the shield working. We could easily have hooked up 2 servos to this. We could hook up 4 motors. As you can see, the wiring's pretty simple. I hooked up wires 1, 2, skip 1, 3, 4, power in, and then the pins you don't have to really set because they're built in, going right into the Ono, and the AF library takes care of the pins. So that is, that's basically it. We've done all the motors. There's only one motor that we haven't done, which is fairly easy to do. I'm going to unplug this, and I'm just going to do it because I'm going to do it in the most crude fashion that you do a motor. So we've got our little tire motor, and I'm not even going to hook this up because I don't want to hook it up long, because this is not a very capable motor. There we go. The simplest way to control a motor, connected to a battery. And I like this motor. It's got a good sturdy little tire. It's not exactly a precision German-made instrument, but they're so easy. The surface is relatively flat. You can hot glue it, Gorilla Glue it into your projects, and it's simple. The only thing I find with these is that this point right here is a little bit weak, so I like to put in my own wires and do a little heat shrink just to keep this whole area a bit more solid. And you can see I threw a little hot glue down there because in just the normal wear and tear I find these wires break off very quickly, so it's a little bit of an upgrade that I do to all these motors. And that's it. Got a gear coming out of either side, or a post coming out of either side, so that might be one of the easiest motors to use. Anyway, I guess I'll do one quickie rundown. DC motors, fairly powerful, cheap, simple. Stepper motors, very precise, but they can lose tracking position. And servo motors, which are much more precise in the way of you can set it to a position and it will generally return always to that position. But they can't go round and round, or at least this one can't. Some can. Those are much more expensive. Ones that can go all the way around and around. but you wouldn't use this so much for powering a motor car's tires as you would the steering, for instance, very commonly found in remote control vehicles for powering wing or moving the wing ailerons and flaps. Well, most little RCs don't have flaps, but rudders, elevators, so on and so forth. Now, one motor we haven't covered, and I will cover this in another tutorial, is what's called a brushless. This one here it has 3 wires. It ties into a thing called an ESC. This basically allows you to control a whole lot of power coming from a whole pile of LIPO cells. Quite a bit of power can pour into this because this kind of motor is capable of holding up a quadcopter, and it's spinning at an ungodly speed, and you need to be able to very precisely control the speed. It's brushless because if it was brushed like one of these at those number of revolutions, it would just wear the brushes out in no time. And but inside here is both circuitry for handling all that power, distributing it in very interesting patterns to the 3 wires here, which then talk to a bit of an interesting set of windings in here. It's this interesting motor. You can see the outside of the motor is actually what's rotating. And you talk to this with an Arduino. So we'll do this one next because quadcopters and whatnot are certainly an interesting part of robotics, and also even in very fast remote control cars. They'll typically go with a brushless rather than a series of DC motors. These make for quick and dirty projects, but for something that's got to really scoot, this is the way to go. So yes, so we've done MOSFETs for controllers, very simple, very elegant. We've done these kind of controllers. They take care of an awful lot for you. This kind of controller takes care of the most for you. And the L293D, where you have to do a lot of wiring, but it is really cheap. And if you're going to be wiring this into your own boards and stuff, this is going to keep things very small, but it's not very capable. And that's it. And then the last motor, which I've hidden somewhere, that we did way back at the beginning, was the big drill motor. Here it is. And a very powerful motor, which clearly means you need a powerful bit of controlling hardware. So you would not control such a motor with the L293D, nor this. And even this would be starting to push out to its limits. You might want to go more purely with something like the MOSFET or whatnot. And yeah. And that is it. Now, one controller I just decided not to do because it doesn't reflect on the Arduino is this guy. But there's lots of controllers like this where you get quite a few amps can pour through this. Forget how many watts this can do, 100 watts or more. Maybe 50 amps, might even be a lot. Might be 250 watts. Anyway, it's a lot of power can go through this. And but that's not really Arduino related, and I like to do things that are robotic and Arduino-like. Anyway, if you have any questions, it's been a long video, probably I think this is my longest by far. If you have any questions about motors, feel free to ask. My last motor video, which only covered this module, seemed to go nuts. So people seem to like motors, so and I have lots of questions because any kind of cool project involves motors. People, I guess, don't like sensing, they like just moving.